In the previous lecture, we finished chapter 3, which is about double integrals. We now have triple integrals. It's a new chapter. It's all about triple integrals. In this chapter, we talk about these topics: triple integrals in Cartesian coordinates, triple integrals in cylindrical coordinates, triple integrals in spherical coordinates, and also moments and center of mass of solids. Here, the last part is the application of triple integrals. We talk about these 4 topics in this chapter. The last one is the applications of triple integrals. First, we have triple integrals in Cartesian coordinates. We say, let G to be this region, to be x, y, z, where x between A and B, and y between C and D, and z between K and L. If f of x, y, z is continuous on the region G, then the triple integral of f of x, y, z over the region equals f of x, y, z, first with respect to z. Z is from K to L as it's written down here. Z is from K to L, and then dy, y is from C to D, and then dx from A to B. This is the limits of y, and these are the limits of x. Here, if all lower and upper limits are constants, if these all are constants, we can change the order. We can change the order of the integrations without changing anything. Just change the order, and then the limits. That's all. For example, if we have the triple integral of, let's say, x squared plus y squared plus z squared for dz, dy, dx. Let's say from -1 to 1, 2 to 3, and -2 to 2. That means here z is from -1 to 1, y is from 2 to 3, and x is from -2 to 2. If you can change the order of this integration, the function is x squared plus y squared plus z squared. For here you have triple integrals. If we take dy, dx, and dz, we just change the limits. Okay. For y, we have from 2 to 3. If all are constants, we can do this. Okay. X is from -2 to 2, and z is from -1 to 1. That's all what we do if all lower and upper limits are constants. Now, we say the triple integral is the volume of this solid. We have this solid, the triple integral. Here, x is from A to B, y is from C to D, and z is from K to L. Okay, this is the shape that you could get from these lower and upper. This is the solid, which is bounded by x is from A to B, y is from C to D, and z is from K to L. This is the solid. We say the volume of a solid G is given by the triple integral over the region. It's only the triple integral. Here the function is 1. We take the triple integral for 1, dx dy dz, or dz dx dy, or dy dx, in any order if all lower and upper limits are constants. Okay, that's the volume. That's for volume. We don't have functions here. We just have 1. We say, we suppose f of x, y, z is continuous on this region, on this this solid x, y, z, where x, y and rxy. That means it's on the plane xy. It's on the plane xy, and z is from the function of xy to another function of xy. We say here r of xy is the projection of the solid. For example, if we have this solid, its projection on the xy plane. It's project what up? Okay, the projection of G on the xy plane is denoted by r of xy. We say finding the volume of this solid, finding the volume of this solid is the triple integral for f of xyz over the solid, over the region. Okay, here we say it equals to, it's given that z is from a function of xy to another function of xy. That means we say the integration of the function for k1 of xy to k2 of xy, dz. We first take the integration with respect to z. Since z is from a function to another function, so that's why we must take the first integration with respect to z. Okay? And z is from k1 of xy to k2 of xy. This is the first integration. Then we have dA over the region xy, over the region r of xy, over this region. We are going to find x is from this point to that point, and y is from this to that. Okay? It's how to find the double integration of a solid or for a function. It's the double integration for this function, where z is from a function of xy to another function of xy. If the projection is on xy plane, if the projection is on yz plane, sorry, yx plane, this is the projection. We have this solid. Okay, we have the solid as projection on xz plane. Here, if y is from a function to another function, is from a function to another function, and x and y in this projection, x and y is in this projection. That means here we take the first integration with respect to y. We must take it with respect to y because y is from a function to another function. Even in the double integrations, we said first we take the integration with respect to that variable, which is from a function to another function, and then we take the second integration with respect to that variable, which is from a constant to another constant. But here y is from a function to another function. That means we should take the first integration with respect to y, then the second and third integration with respect to x and z, or z and x over the region xy, r of xy. And if x is from a function to another function, in this case we must take the first integration with respect to x, and the third and second integrations with respect to y and z, or z and y. Here the projection, in this case the projection is on yz plane. It's on the yz plane. Here we have some examples. First one, it says evaluate this integration. Let's do it. To evaluate this integration, let's first write down the triple integration. First one, the integration from -1 to 1, integration from 0 to 2, integration from 0 to x. As you see, here we have x squared dy dx dz. Here the first integration is with respect to what? The first integration is with respect to y. Yes, this is for y. We take this integration first. Okay, the integration of x squared with respect to y is x squared is a constant. So it is y times x squared, is it? You see the integration, let's say 3 dy. It equals to what? 3y, is it? And here, when we take integration with respect to y, x squared is a constant. That means it's x squared times y. The integration is we still have two integrations. -1 to 1, 0 to 2. For x squared y from 0 to x, dx, dz. Now, we first replace y by x, then we replace y by 0. It equals the double integration, -1 to 1, 0 to 2, for x cubed minus 0. It's still x cubed, is it? Here, when we take integration with respect to y, when we replace the lower and upper limits, we just replace y by the lower and upper limits. And here, the lower limit is 0, and the upper limit is x. If we replace first y by x, then y by 0, we get x cubed. dx, dz. It equals. Now, we take an integration with respect to x. We take an integration with respect to x. And it becomes integration from -1 to 1. For integration of x cubed with respect to x is x to the power 4 over 4. X is from 0 to 2. Then we have dz. We still have dz. And it equals to the integration from -1 to 1. First, we replace x by 2, then we replace x by 0. If we replace x by 2, we get 16 over 4 is 4. dz. When we replace x by 0, we get 0. And the result is integration of 4 dz, sorry, equals 4z. From -1 to 1. And it equals to 4 minus -4, which is 8. Here, the volume or the result of this triple integration is 8. This is 8. Okay, is that easy? For the second one, it says sketch the solid bounded by this plane and x equals 0, y equals 0, and z equals 0. First, let's draw the region, the solid. Okay, x plus 2y plus 3z equals 6. This is the second one. And also, x is 0, y is 0, and z is 0. We should draw the solid which is bounded by x plus 2y plus 3z equals 6, and also x is 0, y is 0, and z is 0. Let's draw it. To draw the graph of a function with 3 variables, we put each variable to be 0 in each case. I mean, each time we let a variable to be 0. We say let x to be 0. What we get? Here we get 2y plus 3z equals 6. It's a linear equation. So the graph of this linear equation, this is y, that's z. It's only a line. If y to be 0, if z to be 0. If y to be 0, z is 2. So the point is 0 and 2. If z to be 0, y is 3. So the point is 3 and 0. We just plot these 2 points on the xy plane. 0 and 2 and 0, 3 and 0. This is 3 and 0. And this is 0 and 2. We just join these 2 points, and then we expand the line. This is the graph for the first case, if x to be 0. And if y to be 0. If y to be 0. Let y to be 0. If y to be 0, we get x plus 3z equals 6. Here we do the same. If x to be 0, if y to be 0, if z, sorry, if z to be 0. If x to be 0, z is 2. If z to be 0, x is 6. So the points are 6 and 0, and also 0 and 2. We have these 2 points. We plot these 2 points to sketch the graph of x plus 3z equals 6. This is x and this is z. 0 and 6 and 0. This is 6 and 0. 0 and 2. We join these 2 points, then we expand it. This is the graph in the case of x, y to be 0. And we let z to be 0. We get x plus 2y equals 6. Here, if x to be 0, if y to be 0, for sketching the graph of a linear equation, we just let each variables to be 0. Then we get 2 points. After finding the points, just plot the points, then join them. You get the graph. Here, if x to be 0, y is 3. So the point is 0 and 3. If y to be 0, x is 6. So it is 6 and 0. We plot it. 6 and 0. Yeah. This is x, it's y. And this one is 3. This is 2. But here it's 3. Okay. And this is 3 and 0. 3, which is 0 and 3. Okay. These are the graphs. Now we join these all graphs on the XYZ plane. On the XYZ plane. Let's join these all together. We have X, Y, and Z plane. Between Y and Z, between Y and Z, we have this graph. It intersects Y at 3 and it intersects Z at 2. Yes. It intersects Z at 2 and Y at 3. Y at 3 and Z at 2. We join these two. We join these 2 points. Okay. And also draw the graph between X and Z. It intersects Z at 2 and X at 6. This is 6. 1, 2, 3, 4. Yeah, that's 6. This is the graph. And we have a graph between X and Y. It intersects Y at 3 and X at 6. So it's from 3 here to 6 here. Let me use another color. Let's use black hole. That's it. That means this is the graph of this function, this plane on the R3. So it's this plane. We have this plane, and it's also bound by 0, 0, 0. It's equals 6. Now, from this we can find y. That's y equals 3 minus 3 over 2z. Is it? That means y is from 0 to this function. Y belongs to 0 to 3 minus 3 over 2z. And if x and y are 0, here, x could be 0, y could be 0 also.
Why can we cheat that? Why can we say that? Why? Y is equal to 0. Then x is 0.
Yeah, you could change it. Just a moment. I'm gonna do it in 3 different ways. We can do it actually in 6 different ways, but it's asked to find only 3 different ways. Here, y belongs to that. Now, x and y could be 0. We replace into the given equation. We get z is 2, is it? If we replace x and y by 0, z is 2. That means z belongs to 0 and 2. Now we write down the triple integral. F of x, y, z. So which integration should be first? X, y, or z? X must be first because it includes 2 independent variables. So it's from 0 to 6 minus 2y minus 3z. This is the x. And the second is y. From 0 to 3 minus 3 over 2z. Then z is from 0 to 10 to 2. This is dy dz. This is one way for expressing the triple integral. Let's do it another way. If we use another way, here we first found x, but now we choose y. Okay, we choose y. Let's take y first here. We say from this equation, we can say y equals 3 minus x minus 3 over 2z. Say, let me write down the equation. X plus 2y plus 3z equals 6. And here, x equals 0, y equals 0, and z equals 0. From this, y equals to 6 minus x, so 3 minus x over 2. 3 minus x over 2 minus 3 over 2z. Is it? We move x and 3z to the right hand side, and then dividing both sides by 2, we get it. And then we say y belongs to what? Y is 0 here, and y is this function. That means from 0 to that function, which is 3 minus x over 2 minus 3 over 2z. And here in this function, y could be 0. Y could be 0. We replace y by 0. What we get? X plus 3z equals 6. And here we can find either x or z. Okay, let's find x. X equals 6 minus 3z. 6 minus 3z. That means x belongs to what? X from 0 to that function. From 0 to 6 minus 3z. How about z? X, we replace x and y by 0, and z is 2. That means z belongs to 0 to 2. And the triple integral is First we have dy. First we have dy. It's f of x, y, z. Y is from 0 to 3 minus x over 2 minus 3 over 2 z. And then we have dx. X is from 0 to 6 minus 3 z. And z is from 0 to 2. As you see, here we have two different types of the triple integrals. Now, we first find z. Okay? Then x and y. And in each case, here we have three cases. And in each case, we can have another case. In this case, we can have another case. Here, we said x equals 6 minus 3z. So if we find z here, I mean, if the second integration is with respect to z, say z equals 2 minus x over 3. That means z is from 0 to that function. Then the last integration with respect to x. If x and y are 0, if y and z are 0, so x is 6 in the given equation here. If y and z are both 0, we get that x is 6. That means x is from 0 to 6. Here we can find 6 different ways for expressing that triple integral. And the last one for yourself. Okay? Last one, next homework. Okay? I have done 2 of them. Do the last one by yourselves. Okay? Yeah, for z. But actually, we can do it in 6 different ways. Six different ways. Because each of these cases is 2 cases. How? Here, we said, for the first case. In the second step, we said y equals to this one, to a function of z. So if we say z equals to a function of y, so it's in the case also. That means we have 6 cases. Okay. Let's do the next example. It depends on the question. Here, it needs only 3. Only 3. Okay. If it asks for all the types, you should write down all. But it's so easy. It's only asking about writing down the triple integrals, not calculating it here in this example. In the third one, it says use triple integrals to find the volume of the solids bounded by the given surfaces. For I, we should find the triple integrals. We should use triple integrals to find the volume. Before we write down the rule of volume. We say the volume of a solid is the triple integral over the region. For 1, we have no functions here. Okay, we have this example. For I, I. It says the solid is bounded by z equals 9 minus x squared. Z equals 0. Y equals 1. Y equals 2. Okay. Z equals 9 minus x squared. Here, the most important thing here is how to find the limits of the integration. We don't need anything else. After finding it, just take the integration. That's all. Okay. Z equals 9 minus x squared. Z equals 9 minus x squared. Z equals 0. Y equals 1. Y equals 2. It says find the solid which is bounded by these functions. these planes also. Here, y, for y, we have both lower and upper limits. We have no problems with y. And for z also, z is 0 to this function. Here, y belongs to 1 and 2. Z belongs to 0 to 9 minus x squared, is it? Okay. How about x? We say z could be 0. We replace z by 0 and we find x values. We say let z to be 0, then 0 equals 9 minus x squared. So you can say x is plus minus 3. That means x belongs to minus 3 to 3. This is the lower and upper limits of x. Now we have the lower limits and upper limits for all the variables for x, y, and z. Now we can write down the triple integral for finding the volume. We say v equals the triple integral for 1 d. Which one should be first? Z, because z, in the limits of z we have functions. That's why z must be first. No, but we must first write down the function. Okay, dz, z from 0 to 9 minus x squared. Then we can write down x or y, because both are constants. Let's see y. Y is from 1 to 2, and z is from minus 3 to 3. dy dx. That's all. Now we find this triple integral that will be the volume of the solutions bounded by those four functions. We say v equals. First, we take the integration with respect to z. So you get the integration from minus 3 to 3, integration from 1 to 2, then z from 0 to 9 minus x squared dy dx. This integration is here. We first replace z by 9 minus x squared, and then we say minus, we replace z by 0, which is 9 minus x squared. It equals to the double integration from 1 to 2 and from minus 3 to 3 for 9 minus x squared dy dx. Okay. Now we take another integration with respect to y. We take integration with respect to y, and we get 9y minus x squared y. It equals to the integration from minus 3 to 3. 9y minus x squared y from 1 to 2. We first replace y by 2, then we replace y by 1. We don't replace x by anything, because here we took the integration with respect to y. It equals to v equals the integration from minus 3 to 3. If we replace y by 2, we get 18 minus 2x squared. Then minus. If we replace y by 1, we get 9. This is 9. We get 9 plus x squared. Let's first write down, and then we do it another time. dx. Okay, this is true. Yeah. Here we first replace y by 2. We get 9 times 2 minus x squared times 2. We get 18 minus x squared. Is it? For that step, you have no problems. If you replace y by 1, here we say 18 minus 2x squared minus If we replace y by 1, we get 9 minus x squared. If we enter this negative sign to here, it becomes minus 9 plus 2y plus y squared. I'll just write down the result.
So we have x squared minus x squared.
It equals to the integration from minus 3 to 3, 9 minus x squared. Then dx. Valid. Now we take another integration with respect to x. To take integration with respect to x, what we get? It's 9x minus x cubed over 3 from minus 3 to 3. First, we replace x by 3, then we replace x by minus 3. If we replace x by 3, v equals 27 minus 9. Okay, because 3 cubed is 27, dividing by 3 is 9. Then minus. Here we get minus 27. If we replace x by minus 3, we get minus 27. If we replace here plus 9. Is it? Okay. Now we insert this negative sign. But before, let's simplify this. It equals, this equals 18 minus 18. It equals 36. That means the volume, this unit cubed, because it's volume, that's why it must be cubed, not squared. So the volume is bounded by those functions is 36 unit cubed. Here, the important step here is how to find the lower and upper limits. After doing that, others are so easy. Just say integrations. Okay. That's for the first one. For the second one, we say find the volume of the solid bounded by 0, x is 0, y is 0, z is 0, and 3x plus y plus 6y plus z equals 6. It's the same as the above one. It's the same as this one. It's similar to this one actually. Only the coefficients of x, y, and z are changed. Let's do it. X, y, z are 0. 3x plus 6y plus z equals 6. 3x plus 6y. For double I, we say 3x plus 6y plus z equals 0. And x is 0, y is 0, z is 0. It says find the solid which is bounded by these planes. Here, from this, look, the lower limit of each variable is 0. It's given that here. X is 0, y is 0, z is 0. The lower limit is 0 for each x, y, and z. We just need to find the upper limits. Let's solve the first one for z. We say z equals 6 minus 3x minus 6y. That means the upper limit of z is this function. The upper limit of z is this function. That means z belongs to 0 to 6 minus 3x minus 6y. And if z is 0 here, what we get? We get 3x plus 6y equals 6. If z is 0, we get this. And from this, we can solve this for either x or y. Both are true. For both are true. Let's solve for y. Let's solve for x. Okay? And from this, we say x is 2 minus 2y. Is it? We divide both sides by 3 and you get that. That means x belongs to 0 That's the lower limit. And the upper limit is 2 minus 2y. How about y? So if y to be 0 and z to be 0, if z and y are z and x, sorry, if x and z are both 0, what we get? We get 6y equals 6. Is it? Here, if x and z are 0, we get that 6y equals 6, so y equals 1. That means the upper limit of y is 1. X belongs to 0 to 1. So which integration should be first with respect to z? Because in z we have two independent variables. We always first from the function which has most independent variables, and then to the constants. Okay. So the triple integral, as since that's about finding the volume, our function is 1. The first integration should be with respect to z, and the second should be with respect to x, and the third one with respect to, sorry, this is z, this is y, sorry, and this is y. Y is from 0 to 1. X is from 0 to 2 minus 2y. Z is from 0 to 6 minus 3x minus 6y. So let's find it. The integration of 1 dz with respect to z, it equals z. And we get the double integration from 0 to 1, from 0 to 2 minus 2y. For z, from 0 to 6 minus 3x minus 6y dx dy. If we replace z by the upper and lower limits, we get 6 minus 3x minus 6y. It equals, so the volume is that. Volume equals the double integration from 0 to 1 and from 0 to 2 minus 2y. For 6 minus 3x minus 6y. Then dy. We take the integration with respect to y. Integration of this function with respect to y is 6y minus 3xy minus 3xy squared. Sorry, it's dx and sorry, it should be dx and dy, because we must do that in the same order which we have written down. It must be dx, sorry, and then dy. To find the integration of this function with respect to x is 6x minus 3 over 2x squared minus 6yx. This integration from 0 to 1 for 6x minus 3 over 2x squared minus 6xy from 0 to 2 minus 2y. Then you have only one more integration. Now we replace each x by 2 minus 2y. We don't replace y by anything because our integration is with respect to y, to x that we took. We say v is integration from 0 to 1. The integration from 0 to 1 for here, you say 12 minus 12y minus 3 over 2, 2 minus 2y squared. Is it? Minus 2y plus 2y squared, so 12. Is it? It's true. It should be true. Because here we replace x by 2 minus 2y. We have y and multiplying by 6 is 12. Here, minus 12y, so these two are going to be added. This is dx, so dy. Now we simplify v equals the integration from 0 to 1. We have 12 minus 12y. Minus 12y is minus 24y. Minus 3 over 2 minus 2y squared plus 12y squared dy. Now we take another integration with respect to y. To take the integration with,
Isn't it easier if you do the square root of 2 minus 2y?
if you expand that square bracket, yeah, you can.
It's easier.
Yeah. But here, this is also easy. It's easy also. Okay. Both are easy, no worries. It equals the integration of 12 is 12y. The integration of 24y is 12y squared minus 12y squared. The integration of 2 minus 2y squared. We must have the integration of the function inside the bracket, which is minus 2. We multiply it by minus 2 and dividing it by minus 2. Okay. And we get minus becomes plus 1 over 4 2 minus 2y cubed. Okay, look, the integration of this 2 minus 2y squared. If we have the derivative of the inside the bracket, which is minus 2 divided by minus 2. The integration of the bracket is we just add 1 for the bracket dividing by the new exponent. We get minus half of 2 minus 2y to the power 3 dividing by 3. And if you multiply 3 over 2 by this, what we get? We get 1 over 4. Is it? 3 and 3 are cancelled out, and we get minus half multiplying by minus half is 1/4.
1 over 2 multiplied by
Minus 1 over 2, and here we have a negative sign also. It becomes positive.
yeah, but let me say multiply.
3 and 3 are cancelled out. And here 12y become it's not 12y squared is 4y cubed from 0 to 1. You replace y by 1, then by 0. If replaced by 0, all terms become 0. When you replace by 1, this is 12, this is 4, is this 12, and that's minus 12. These two are cancelled out. Okay, and you replaced by 1, this is 0 also, and you get 4 only. It's 4. So the volume of the region of the solutes bounded by those functions is 4 unit cubed. You know, the only important thing here is to write down these lower and upper limits. Others are so easy. It's only taking integrations. Okay.
I need to write 2 minus 2y. Yes, sir.
2 minus 2y cubed so this squared. Here we have, I said we have minus 3 over 2. 2 minus 2y squared. Okay, so the derivative of 1/4 for this one must be that. Okay, let's check. Derivative of this function is, we say if we have f of x to the power n, and its integration is n times f of x to the power n plus 1 times f prime of x. We apply that rule here. Let's do it. We say we have 1/4 multiplying by. We bring the numerator to here. And so the exponent to here is 3 times. We reduce the exponent by 1, which is 2 minus 2y to the power 2. Multiplying by derivative of the function here, which is minus 2. Look, it becomes, these two are cancelled, it's 2. And here we have a negative sign. Multiplying by 3 is minus 3 over 2. 2 minus 2y squared. Look, we got this thing. So let's take a break for 10 minutes. We now have another example. It says find the volume of the solid which is bounded by these planes. These functions. Z equals z plus x squared equals 4, y plus z equals 4, z equals 0, y equals 0. Here, the lower bounds for y and z are given. So you just need to find the upper limits. And for x, we have nothing. We have neither lower bound, lower limit, and upper limit also. But here we have given that z is 0, and we have x in only one function, which is z plus x squared equals 4. Z plus x squared equals 4. But we have given that z is 0. If we replace z by 0, what we get? We get x squared equals 4. That means x squared, or x, is plus minus 2. That means we got both lower and upper limits of x, which is minus 2 and 2. So x belongs to minus 2 and 2. The lower limit of the integration with respect to x is minus 2, and the upper limit is 2. That's the lower and upper limits. And then for z, here you have z in two functions. We have z in these two functions. What we do, we are going to solve these two functions simultaneously. We say, by adding these two functions, adding z plus x squared equals 4 and y plus z equals 4. We don't know which one should we use. Z equals y minus 4 minus y, or z equals 4 minus x squared. We don't know. That's why what we do, we should solve both together. By combining these two functions, we can get the upper limit of z. And these two, the sum of these two functions is 2z plus y plus x squared equals 8. We just add these two functions. We just add left-hand sides together and right-hand sides together. Now, we say z equals 4 minus y over 2 minus x squared over 2. Is it? Can you say that? Here, we move y and x squared to the right-hand side, then divide both sides by 2. We get that. That means z belongs to what? We have given z is 0 and 4 minus y over 2 minus x squared over 2. This is the lower and upper limits of the integration with respect to z. Now, we need to find it with respect to y. We have y in only this function, and z could be 0, and z is 0. Z is 0. Here, x is 4. Oh, sorry, y is 4. If z, then from y plus z equals 4, we get that we get y equals 4. That means y belongs to 0 to 4. We have the lower and upper limits for the integration with respect to x, y, and z. Now, what we do, we're going to find the integration or find the volume. we have a triple integration. Which one should be first? Z. From 0 to 4 minus y over 2 minus x squared over 2. This is dz. Then what should be the next? It could be x or y. Both are possible to be the second one because both are constant. I mean, both lower and upper limits for each x and y are constants. Let's take y. It's from 0 to 4. This is dy. Then from -2 to 2. That's for x. Now we take the first integration with respect to z. That equals the integration -2 to 2. Integration from 0 to 4. For 1 dz is z. From 0 to 4 minus y over 2 minus x squared over 2. Then dy dz. Dy dx, sorry. Now we replace z by the upper limit, then minus we replace by the lower limit. That equals v, that's the volume, equals that. It's the integration from -2 to 2. And then from 0 to 4, for 4 minus y over 2 minus x squared over 2. Then dy dx. Now we take another integration for the function with respect to y. If we take the integration with respect to y, we get integration from -2 to 2 to 4y minus y squared over 4 plus xy squared over 2. From 0 to 4 dx. We have only one more integration with respect to x. Okay, we replace y by 4, then by 0. When you replace y by 0, all terms become 0. We just replace y by 4, and you get v equals integration from -2 to 2 for 16 minus 16 over 4 is 4 plus 16 over 2 is 8. Then dx, it equals to the integration from -2 to 2 for 16 minus 4 is 12 plus 8x dx. Now we take integration with respect to x, and it equals to 12x plus 4x squared from -2 to 2. We first replace x by 2, then by -2 was 48. The result is 48. Okay? The result is 48 unit cubed. We replace x by 2, and then we replace x by -2. When we replace x by 2, that is 24 plus 16 was 40. Okay, and when we replace by minus, and you have a negative sign also, it becomes 24 plus 24 minus is 40. 24 minus 16. You have 24 minus 16 plus 24 plus 16. This one cancels. 24 and 24 is 48. So the result is 48. Okay. Let me clean this one because I have it down above. That's the complement of the previous example. So now we have the triple integrals in cylindrical coordinates. For the triple integrals in cylindrical coordinates, we replace each x by r cosine theta and y by r sine theta. And we say tan theta equals y over x. If we have the term of x squared plus y squared, we replace by r squared. We replace by r squared. And the same as the previous one, if this vertically and in the other side also. Here, we say if z, we say the triple integral for f of r, theta, and z dv equals the double integral over the region r and the integration of the function with respect to z from k1 of r theta to k2 of r theta. Here z is a function of r and theta. Z is a function of r and theta. It's possible if we have z in the function to take its integration, because the first integration is with respect to z. But it's impossible to have x and y, even for the function and for the limits. For the limits, we must only have, trigonometric functions. It's possible if we have trigonometric functions, because it's a function of theta and r. And also, it's possible to have constants. Okay? We must only have theta, r, and constants for the limits. And for the function, we must only have r, theta, and z. We must have no x and y. Look at this example. It's so easy. In the example, in the question, it says by using cylindrical coordinates, so you must convert each xy terms to r and theta. Okay, it says find the volume of the solid bounded by z equals x squared plus y squared, and x squared plus y squared equals 4, and also z equals 0 by using cylindrical coordinates. Here we have given that z equals, it's for the first one, z equals x squared plus y squared, and z equals 0. That means the limits of z is from 0 to x squared plus y squared. But we said that x squared plus y squared is r. That means z equals r, and z equals, so it's r squared. Z equals 0. So z belongs to 0 and r squared. Is it? Look, we said before x squared plus y squared equals r squared. And if you have x terms, x replace x by r cosine theta, y by r sine theta. So here we say this from 0 to r squared. Now, the other function, it says x squared plus y squared equals 4. Here we draw the graph for this one to be easier to indicate the other limits. Here, this is r and theta, this is x and y. Here, the radius of this circle is, what's the radius of this circle? It's 2. That means the radius is starting from the origin to where? To here. It's 2 units. To here, it's 2 units. To here, it's 2 units. To here, it's 2 units. From all sides to the boundary is 2 units. 2 units. That means r is starting from 0 to 2. R belongs to 0 to 2. How about theta? Theta is starting from there to itself. It means theta belongs to 0 to 2 pi. Is it? We talked about this before in double integrations. Okay, in polar coordinates we talked about this. Now we have r, theta, and z, and we should check the integration. We say dz, dr, d theta. So the volume V equals the triple integration of R dz dr d theta. We always write down R. As before, we said it's R dr d theta in double integration. Here, we always write down R dz dr d theta. What's the limits of z? From 0 to r squared. What are the limits of r? From 0 to 2. And the limits of theta? From 0 to 2 pi. Just find this integration. Find integration of r with respect to z is here. The first integration is with respect to x to z. It's from 0 to 2 pi and from 0 to 2 for rz from 0 to r squared dr d theta. Now we take an integration with respect to r. If we replace the lower and upper limits, here we get r cubed. It equals the double integration from 0 to 2 pi, from 0 to 2 for r cubed dr d theta. Okay. Now integration of r cubed with respect to r is r over 4 to r to the power 4 over 4. It is from 0 to 2 pi for r to the power 4 over 4. From 0 to 2. We replace r by 2, then by 0. When we replace by 0, it's 0. And when we replace by 2, we get 4. This is d theta. It equals from 0 to 2 pi for 4 d theta. And equals to 8 pi. Okay. This is the volume. Here is 4 theta. We replace by 2 pi and by 0. And we get 8 pi. That means the volume was bounded by these two functions by using the cylindrical coordinates. It is 8 pi. It is 8 pi. Okay. That's all about this example. We have 2 more examples. It's for tomorrow.